There are indeed many definitions of engineering. To the pessimist, the glass is half empty. To the optimist, the glass is half full. To the engineer, the glass is twice as big as necessary. Let me state at the very beginning that Robert Morris University has a solid engineering past, an excellent engineering present, and a very bright engineering future. The ABET definition of engineering is more focused, particularly because of the emphasis on engineering judgment. Most engineers will also agree that benefit to mankind ranks high on their list of goals. Before the French Revolution of 1789, there were officially only military engineers. Non-military engineers later began to be called civil engineers. With the Industrial Revolution of the 19th century, mechanical engineers gained importance, and then electrical engineers, and so on. The number of majors in engineering is increasing as new fields of study develop and open up. The emphasis currently is both on specialization and on interdisciplinary topics. The influence of engineering in the last 50 years has become both widespread and important. Progress in medicine often depends these days on the techniques of bioengineering. The amalgamation of engineering approaches with management techniques has also developed to a very high level. Aerospace engineering is one of the most challenging of engineering disciplines. The weight-to-strength ratio for airplanes, the theory of flight, the properties of new non-metallic materials all feature prominently as subjects for research and practical applications in the area of aerospace engineering. As a discipline, agricultural engineering may currently lack glamour, but it is a necessary and useful area covering structural as well as mechanics aspects related to agriculture. Architectural engineering aims at a synthesis of aesthetics and calculation. While the goals of architectural engineering are praiseworthy, the mixture of a subjective discipline like architecture with a mathematically based engineering program does not often yield favorable results. One of the most simple biomedical engineering tools is the blood pressure measuring kit. At the other end of the scale, we have tube-like coronary stents. All mechanical, electrical, and electronic devices used to help or replace body parts owe their existence ultimately to biomedical engineering. Chemical engineering is part and parcel of our daily lives, from the preservation of food to the paint on our automobiles. No wonder they say everything begins with chemistry. Civil engineering is the oldest engineering discipline. It is intimately connected to civilization. Our living space is built by civil engineers, so are our roads and bridges and dams. We take the civil engineering environment for granted, without appreciating the hard work that has gone into it. Computer engineering is currently the most popular member of the engineering fraternity. Computers continue to develop at an amazing rate, so the glamour attached to computer engineering is not likely to fade anytime soon. It takes a power cut after a hurricane for most people to understand how vital electricity is to us all. However, electrical engineering is important also for computers, for cell phones, and even for biomedical devices in hospitals and elsewhere. Environmental engineering would not have been so important and critical a discipline if our civilization did not ruin the environment and also produce mountains of waste every year. Industrial engineering is actually the study and improvement of engineering systems, both at the macro and micro levels. Cost optimization in manufacturing and production, and also the impact of human factors on engineering design also comprise part of this discipline. Marine and ocean engineering deals with all types of sea-going vessels, but these days there are great challenges in the design of offshore drilling platforms that extend to the ocean bed, and also the design of oil or gas submerged pipelines. Special purpose materials such as Teflon or Kevlar or fiber-reinforced polymers are often superior for certain applications when compared with more conventional materials. Materials engineering is an area with a great future. Today, mechanical engineering goes well beyond just machines and engines. Many processes in mechanical engineering, especially those dealing with production, are now fully computerized. All heating and cooling systems also form an important area in mechanical engineering. Mining engineering enables efficient utilization of the Earth's mineral resources, both for fuel as well as for the production of a large variety of metals. All subterranean construction also needs the input of mining engineers. Nuclear engineering deals essentially with the production of electricity by means of nuclear fission. However, much work needs to be done in this area before nuclear engineering can provide us with fully safe electrical power. Accidents do unfortunately happen, as in the case of the 3 Mile Island reactor and the earthquake-stricken reactors in Fukushima, Japan. Fossil fuels lie well concealed within the earth. Before gasoline can be pumped into the fuel tank of your automobile, many engineering processes have to be completed successfully. The location and exploration of oil, the refinement of crude petroleum, as well as the pumping of gasoline through pipelines, all need complex processes that come under the name of petroleum engineering. Just as children leave home and start leading independent lives after a certain age, minor disciplines become major disciplines after they have grown and developed, and are treated as separate disciplines in their own right. Manufacturing engineering is an example. It used to be considered part of mechanical engineering, but is now a new discipline. Logistics engineering is also a new discipline, based on systems engineering, computer applications, management skills, as well as communication techniques. Software comprises instructions to a computer to tell it how to proceed to solve your engineering problem and to give you the answers you require. Software is the computer's language, if you wish to simplify matters. Let us attempt to have a look at the history of engineering over the centuries. Man began living initially with a fire in a cave. However, buildings and structures, initially primitive but later sophisticated, began to come to the forefront, and especially in earlier times, engineering was primarily structural or civil engineering. Recapitulate the overall situation at the start of written human history. Man had to live under the most primitive conditions and often did not know where the next meal would come from. However, this did not prevent man from using brain power to improve his life. Civilization, including agriculture and writing, developed along the banks of great rivers, such as the Nile in Egypt and the Euphrates and Tigris in Mesopotamia. Over 4,000 years ago, the use of engineering methods resulted in the construction of great structures such as the pyramids in Egypt. Ziggurat means rising building in Akkadian, which is a language no longer in existence. Ziggurats go back 6,000 years, and some well-preserved examples, which in their time were used as temples, still exist in modern Iraq and Iran. About 2,500 years ago, the Greeks and later the Romans began to build monumental structures like temples, amphitheaters, and aqueducts for water. Several of these massive engineering works survive to this day. The huge scale of the aqueduct may easily be observed from this slide. Although no engineering calculations survive from that time, builders had apparently found out experimentally that arches were suitable shapes for masonry construction. One of the biggest structures of all time, dating back 2,200 years, is the Great Wall of China. The construction of the Great Wall must have required much skill and the labors of thousands of artisans. Of course, the Great Wall is now a great tourist attraction as well. Leonardo da Vinci of Italy was a versatile genius. His drawings and paintings are priceless, but his contributions to engineering are almost equally great. Here we may observe from the origins of the word engineer that it is intimately related to talent, for which the word is ingenium in Latin. For many centuries, civil engineering was the most developed area in engineering as a whole, because at the time human needs were centered primarily around civil and military structures. Hence, for past centuries, examples of impressive achievement in engineering tend to be large buildings. We have already mentioned that shelter is a basic need for human beings from the earliest times. Shelters, whether primitive or luxurious, need to be constructed according to some logical system. This is where engineering ideas come in. The earliest construction material for man was mud. In the form of sun-dried mud bricks called adobe, it is still used in many areas of the world. Reinforcement is provided for mud with stone, timber, and straw. However, the scope of mud as a construction material is highly limited. The true arch is a structure that carries loads primarily by compression. Most materials are strong in compression but weak in tension. Hence arches have been used over the centuries. According to researchers, it is highly likely that the arch came about as succeeding layers of stone were allowed to jut out a little further. The corbel is thus the earliest form of arch. That a cable works in a manner opposite to that of an arch was discovered only about 500 years ago, during the Renaissance. The strength and efficiency of typical arches improved with developing engineering skills. The level of construction practices also improved, as indicated in this slide. The main function of a truss is to utilize individual load-carrying elements, which are short in length, to produce a stable structure which covers a large span. Primitive suspension bridges of all types have been used for many hundreds of years and can be found today in all parts of the world. When a structural member supports a lateral load, as shown in this slide, where the large stone beam covers the passage, it is subjected to bending and does not behave simply as a compression member. 5,000 years ago, Imhotep was the structural designer for the pharaohs of Egypt. He was responsible for the construction of the first large pyramid in Saqqara with a height of 200 feet for the burial of the pharaoh Djoser. Because of Imhotep's great construction feats, he was given the status of a god in ancient Egypt, and therefore statues of him exist, as shown in this slide. As may be observed, the stepped pyramid is a vast monument of stone. It has a total volume of over 11.5 million cubic feet, which is massive by any reckoning. 1,500 years after Imhotep, the elegance of the stone construction may be observed from the massive columns of the Amenophis temple at Luxor in Egypt. We have to try to put ourselves in the place of those ancient builders. They observed that vertical loads like the weight of a structure were not difficult to support. Loads that were lateral and came from the side led to instability. Hence they chose big broad bases, as in pyramids, for their construction. One early way of getting structural information was by producing small clay models of a large building and applying loads to them. Model testing, such as the wind tunnel testing of scaled-down tall buildings and even airplanes, is routinely conducted today. Yes, but what happened in ancient times if a building collapsed during or after construction? King Hammurabi of Babylon had very tough punishments for builders in those times. If the building collapse resulted in death, the builder would have to pay for this with his own life. In short, it was just an eye for an eye and a tooth for a tooth. The tablets of the Hammurabi Code from 3,700 years ago still exist with the ancient wedge-shaped writing and are to be found in museums. Almost 3,000 years after Hammurabi, Leonardo da Vinci in Italy tested materials to check how much load they could carry before fracture in tension or crushing in compression. 100 years later, but also in Italy, Galileo conducted more elaborate experiments to investigate how beams and columns carried their loads. The simple cantilever, fixed at one end and free at the other, is a basic structural component for balconies. Here Galileo attempted to study the internal stresses produced in a bending test. Reference has already been made to the tensile tests on rods and springs, conducted by Robert Hooke in England about 100 years after Galileo. Almost a century after Robert Hooke, Leonhard Euler of Switzerland studied many problems in engineering. He observed that thin steel rods were strong in tension, but would bend outwards and buckle under low compressive loads, and he solved the problem mathematically in order to calculate this buckling load. Coulomb was a French engineer who made important contributions to soil mechanics, structures, and even electrical engineering. This slide shows his apparatus for the experimental study of torsional vibration. The 19th century in Europe saw the advance of mathematical solutions for problems of deformable bodies. These solutions laid the foundations for what is now called the theory of strength of materials. In a period of time of less than a century, structural engineering calculations have been systematized and computerized. All engineering structures can be analyzed today with great speed and with great facility. The computer is an utterly efficient instrument, but in order to get correct and meaningful results from it, the data fed to it must also be accurate and relevant. A few slides of monumental buildings from the past will now be presented. Breadth of vision, greatness of scale, and minute attention to detail characterize these massive historic structures. The famous building of Santa Sofia in Istanbul has one of the most impressive domes of all. This 1500-year-old building has survived earthquakes and fire and today serves as a museum. Over 800 years ago, stone masons and master builders produced a large and impressive cathedral at Chartres in France, which enthralls tourists and visitors even today. In Southeast Asia, at the same time as Chartres, other builders of genius were constructing the great temple complex of Angkor Wat in present-day Cambodia. The Alhambra, or Red Castle, in Granada, Spain, was the residence of the Muslim kings of Andalusia and is probably the most visited monumental building in Spain today. This building was completed in the 14th century. The Taj Mahal, called a dream in marble, was built by the great Mughal Emperor Shah Jahan in Agra in northern India as a burial monument for his wife Mumtaz Mahal. It took 22 years to be built. Of the Mughals, it is said that they built like giants and finished their work like jewelers. The Sultan Ahmed Mosque in Istanbul is one of the few mosques in the world with 6 minarets. Built by the architect-engineer Sedefkar Mehmed Aga, it is also called the Blue Mosque because of the gentle aura of the blue tiles which cover the interior walls. The Clifton Bridge was opened in 1864 and is the symbol of the city of Bristol, England. The engineer Brunel was only 24 years old when placed in charge of this project. The pace of building construction in the last 100 years has been unprecedented. The high cost of urban land, combined with increasing populations in most countries, has pushed buildings to go higher and higher. High-rise buildings in a severe earthquake zone require special calculations and building techniques. Architects and engineers today possess the ability and necessary expertise to design and construct such high-rise buildings. New buildings in Los Angeles have been successful in withstanding major earthquakes without any major damage or loss of life. Older buildings do not fare as well during earthquakes. As may be observed from this slide, multi-storied buildings are plentiful in the central districts of all American and even foreign cities. San Francisco, also an earthquake-prone area, lives up to its reputation for visual elegance in all respects. Considering that much of San Francisco suffered severely in the great earthquake of 1906, such high-rise construction in San Francisco shows how much progress has been made in this period. Simple box-like buildings are relatively easy to design and construct. However, clients, as well as architects, demand unique features in the buildings of today, resulting in more work for engineers. All over California and all over the United States, high-rise buildings continue to be constructed, even down to San Diego, which is near the Mexican border. Among the famous architects who introduced many features into multi-storied construction was Frank Lloyd Wright, who was born in 1867 and died in 1959. Frank Lloyd Wright is considered the greatest American architect of all time. This is a typical example of a building with external bracing members that contribute to carrying lateral wind and earthquake loads. High-density residential accommodation, suitably designed and constructed for earthquake loading, is a common sight in California, as this slide from the Bay Area shows. An extraordinary and impressive structure incorporating strength, beauty, and elegance is the famous Gateway Arch on the banks of the Mississippi River near St. Louis. The next two slides show the concept as well as the construction of the tall tower designed in Racine, Wisconsin by Frank Lloyd Wright. While for purposes of economy, most tall buildings use a steel framework, reinforced concrete has also been used with much success in the construction of high-rise structures. There is no shortage of interesting building structures which bear testimony to the visions of the architects who conceived them, as well as the designing skills of the engineers who constructed them. This is a picture from Prague in the Czech Republic, with a large reinforced concrete box girder bridge that serves for traffic as well as for subway travel. Famous architects like Kenzo Tange in Japan have designed buildings of many stories that look elegant, are fully functional, and also perform well in earthquakes. Let us have a look at one of the many striking designs produced by Frank Lloyd Wright, the Guggenheim Museum in New York, which he called an inverted ziggurat. Fazlur Rahman Khan was born in 1929 in Dhaka, now the capital of Bangladesh. He took a doctorate at the University of Illinois at Urbana-Champaign and was the structural engineer for landmark buildings in Chicago, like the John Hancock Center and the Sears Tower. He introduced many new concepts of tubular structures. He died in 1982, and in 1998 a Chicago street was named after him. Santiago Calatrava, born in 1951, is an outstanding architect and engineer from Spain, whose exciting designs feature in many countries of the world. Jean Utzon died in 2008 at the age of 90. He was a famous Danish architect who designed many structures, including the Sydney Opera House. However, he had to leave the Sydney Opera House because of much acrimony and bitterness. The Burj Khalifa is 2,723 feet tall and has more than 160 stories. It is the tallest freestanding structure in the world. It was built from foundation to spire in about 5 years, and it has a nightclub on the 144th floor. The trend towards taller and also towards more sophisticated buildings will increase the demand for more and better qualified engineers, civil, mechanical, electrical, as well as materials engineers, software engineers, and other engineers. With the present state of expertise in both engineering analysis and design, there is no excuse for building faulty or inefficient structures. Even for earthquakes, state-of-the-art building codes are available and can be used. The Eiffel Tower held the title for tallest structure in the world for 41 years after it was opened in 1889. It is 1,050 feet tall and contains no less than 2.5 million steel rivets. It is now one of the symbols of the city of Paris and is called the Iron Lady. Gustave Eiffel was born in 1832 and died in 1923. His steel structures are to be found in many countries of Europe and include both buildings and bridges. The Eiffel Tower in Paris took less than 2 years to build. The Golden Gate Bridge is 75 years old. When built, it was the world's longest suspension span, about 3/4 of a mile. It was designed not with a computer but by hand calculations. Since its construction, it has been subjected to structural strengthening. It is today an important San Francisco icon. The statue of Joseph Strauss, with the bridge in the background, is shown in this slide. Strauss was a poet of considerable merit, in addition to being an engineer of great vision. Strauss's own poem, called "The Mighty Task is Done," mentions that the bridge looms mountain high, and it also narrates his own difficulties during the period of construction of the bridge. All engineers, and especially civil engineers, have important social responsibilities. They must build not just for the lucky few in their community, but search out methods and techniques to help the poorer sections of society. Engineers have a very broad spectrum of employment opportunities. They can do scientific research, or do analysis and design, or go into production. There are also many academic and administrative openings for engineers today. Many white-collar engineers are active in research. The difference between scientific research and engineering research is that the latter is geared usually to practical ends. Engineering research often leads ultimately to patents and to new products. Full-scale experimental research is conducted on small products like machine parts and even on large structures like bridges. Structures and buildings are occasionally tested even to destruction. Computer simulation and parametric studies comprise another active area of engineering research. Deciding on the proper aerodynamic shape of a flying vehicle requires intensive computer modeling and experimentation. Research also involves the development of software, both for general purpose applications as well as for specific tasks. Engineers are involved in the preparation and development of all commercial computer programs. Development engineers deal with all engineering disciplines. They are responsible for checking if a research idea can be metamorphosed into an application and perhaps even into a commercial product. Development engineers have to interact with the research engineers to modify ideas in order to make them feasible. Development engineers often bring great experience and judgment to an engineering process. The role of the testing engineers is vital in every engineering application. Monitoring the testing requires special engineering skills. These days, engineering components can range from the micro level to very large dimensions. No engineering product can be put to use without extensive testing of the prototype. A new car model is often subjected to thousands of miles of testing on a closed track for safety and performance. The chicken gun example given in the next two slides indicates how important all parameters are for successful testing. For an experiment to be useful, it may need to be repeated dozens of times. Design is, so to speak, the engineer's bread and butter. The shape, cross-section, material, and weight of a machine component, for example, all these have to be calculated and specified by a design engineer. The efficiency of design enables economical production of machines and equipment. Similarly, safety specifications for each item are also the responsibility of the design engineer. New challenges in engineering and the solution of new problems that emerge with developing technology require analysis for their investigation. These days, most engineering analysis is computer-based. There is a certain logical sequence in many engineering processes that allows them to be fitted into a system or encourages automation of production in whole or in part. Systems engineers facilitate assembly, synthesis, and production of parts and products. Some engineering processes begin with raw materials like plastics or textiles or even scrap metal. In the manufacturing process, manufacturing engineers check on both quality and precision. In addition to engineering skills, manufacturing engineers should have a sound knowledge of inventories and statistics, apart from possessing good personal skills. They say that a small leak will sink a big ship. A minor glitch in an operating system may result in production being halted and a loss of hundreds of thousands of dollars. Operations and maintenance engineers ensure the smooth and continuous running of electrical and mechanical equipment. Sophisticated engineering products, like a mobile electricity generating system, cannot just be purchased off the shelf. Technical support engineers have to supervise the installation and initial working of the system and products, and therefore they fulfill a very important role. If the engineering product to be marketed or sold is costly and complicated, even customer support may need to be provided by an engineer. Thus, a large seagoing yacht may require a marine engineer for customer support. Where the sale of aircraft is concerned, salespeople are usually chosen from qualified engineers, because very often the purchaser's representatives are also qualified engineers. A limited percentage of engineers in all disciplines will ultimately become consulting engineers or consultants. These consultants are usually engineers who have specialized in a particular area. For example, in the law of contracts for engineering applications, or in the design of parking facilities, or in traffic engineering. Independently working consulting engineers are often invited by large companies as inspectors in order to examine the company and to improve the output and efficiency of the engineering organization. After 20 or 30 years as practicing engineers, many technical people find themselves in positions of management or supervision. Engineers should therefore equip themselves with management skills. Particularly in the United States, engineers often study to enter another field, including medicine. There are also lawyers with engineering backgrounds. Engineers tend to be realistic and to keep their feet on the ground. All careers, in theory, are open to engineers.